So, good day to all of you. You can put in place in the day, in the sense that you can put in morning, night, evening as you want, depending on when you are seeing this video. So, if you have followed up to the last one, then in the last one we proved the fundamental theorem of linear programming, which says that if my feasible set is non-empty, then there is a basic feasible solution also, and if I have an optimal solution of the linear programming problem, then there is a basic feasible solution which is also an optimal solution. So, non-emptiness of the feasible set implies the existence of BFS, and existence of an optimal solution implies the existence of an optimal BFS. So, this is a very beautiful fact, because it says that I can always look for vertices. So, simplex method will show you how to go from one vertex to the other in a clever way, so that your function value actually decreases. Today we will keep on a very simple thing to work on. First we will go and look into the notations for the simplex method. See, the approach that I take again is due to Manfred Padberg, and I take it because I love this approach. Of course, everybody does what he loves. So, here there will be certain simplifications of certain notations which will make maybe the writing simpler. We will first write down the notations, and then we will prove two things. First, when I say run the simplex method, how do I know that I have actually reached an optimal BFS and I can stop the process? 2, how do I know that I am actually wasting my time, that the problem is unbounded and I need not bother about solving it. So, these two aspects has to be checked out from certain conditions involving the problem data. And what are those conditions? Number 1, a sufficient condition for guaranteeing optimality. Number 2, a sufficient condition for telling me that the problem is unbounded below. So, once I know these two things, it will be easy for me to actually explain you the simplex method. So, we will only study the notations and these two things today, and in the next lecture we will analyze the simplex method. So, when you write C transpose X here, basically what you are writing C1 I can write this also as, if I take C as a row vector, then I can also write this as Cx. If C is considered as a row vector, you know that C transpose is written, I write it as C transpose because this is C transpose, because C is usually considered as column vector. For simplicity we will write Cx, you can continue writing C transpose X or even C inner product X, does not matter. So, we will again for simplicity write B to be an M cross M submatrix survey. Of course, A has rank 1 and no non-zero rows or columns. So, M cross N submatrix survey, so which is the basis matrix, B is a basis matrix. So, this is our notation. To N, the rest of the matrix, when B is pulled out. So, whatever those columns which are remaining, right. So, when you take off the B, whatever column is remaining is your N, the non-basic part basically. So, I will denote by IB. Do not confuse it with the I or IX that I have used in the last class. This IB is you can put some other symbol if you want, but in mathematics we learn not to get confused with symbols. This is the index position, the first index of the basic variable, second index, third index, fourth index. So, this is called the index set of the basic variable. I will explain why. Why is this sort of strange looking things? Why not 1, 2, 3, 4, 5, 6? Now, what does Ki symbolize? So, Ki is the original column which is now the ith column of B, the basis matrix. And if I just do some explanation by a small example, that will be much clearer. For example, I have a 3 cross 4 matrix. So, it is A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34. Now, this is a 3 cross 4 matrix, and if I assume it to be full rank, all these rows are linearly independent. So, I can choose any 3 columns which are linearly independent. Suppose my basis matrix, this goes in B, this goes in B, and this goes in B. So, my B would now look like the following. Just stack up the rows, nothing else. Now, this is the first position, first column of the basis matrix, this is the second column of the basis matrix, this is the third column of the basis matrix. So, my K1, which is the first position in the first column of the basis matrix, was the first column of the original matrix. Now, K2, so the second column of the basis matrix corresponds to the third column of the original matrix. So, this is the original matrix A, and there you get the basis matrix B. So, and K3, the third column of the basis matrix is the fourth column of the original matrix. So, this is what this notation actually means. So, I will just divide this page a bit. Now, XB denotes the vector corresponding to vector whose components corresponding to these columns. So, XB in this case would corresponding to the basis columns. So, x1 basically xk1, xk2, xk3. So, x1, x3 and x4, this is my basis matrix, and remaining are the non basic part. Now, if you have j element of IB, so Pj denotes the position of the jth variable in the basis. So, P 3 for example, jth variable x 3, his position in the basis is 2, P 3 is 2. Okay. But if you observe also P, what is 3 here is K 2. So, P K 2 is 2. So, in that sense one can write in general P K I is I. So, it tells you that the third variable in the actual setup x 1, x 2, x 3, x 4 is the second variable of the basis matrix. Okay. So, these are certain notations which would be helpful when we will do the simplex method. So, usually ZB is equal to CB B inverse B is the objective value to the matrix basis matrix B. If you have forgotten why it is like this, you know that I can always divide x whole x into xb and xn. See, it should be CB transpose. In usual text it will be CB transpose, but we are just considering CB to be a C to be a row vector. So, it is written like this. So, I can write this as this, x as xb xn, and then you know that A of x is equal to B. So, and A is partitioned into B and N. So, you can write B x B plus N x N is B, and if x n equal to 0, we know that x B and CB transpose B inverse B, which is same as whatever we have written. CB transpose is, we are not writing CB transpose because that is taken to be a column matrix, to be a row vector. So, Z, this is of course a notation for index set of non-basic variables. In this case, what the example given in the previous page, the non-basic variable was x2. So, this consisted of just 2 in the last case. So, x n actually can be written as x j in a short form, but j belongs to x j transpose. In fact, this is, if I write it as a row vector transpose, j belongs to j minus I b. So, there are many ways to write the obviously simple looking things. So, but certain notations are important notations for the simplex method. First notation is B bar. Okay, this is the transformed right hand side or x b basically, B bar is x b. Because you are operating B inverse on B, so we just write this as, this is nothing but the first part, this is the B bar of the BFS. It is also called the transformed right hand side. And now C bar, C minus C B, actually books would have C B transpose B inverse A, but as per I want to remind that this is a row vector, we have just taken for simplification of the notation. This is called a reduced cost coefficient. There is a cost coefficient C and I am reducing the value of the cost coefficient by this amount. This automatically comes, this thing naturally appears. You might think that how are you suddenly bringing up this fact, bringing up this number, but no, actually people try to figure out certain thing, how to get optimality, how to get unboundedness. So, mathematics is always guess and test. These things are not written very in the very beginning, when Danzig did not came to this, or rather I would say Danzig really did not bother much about the matrix notation, but when the matrix notation came, nobody just wrote it down like this. People were actually trying to figure out under what condition there will be an unboundedness, under what condition I will have optimality. Then these things appeared quite naturally in the expression, and hence conditions had to be imposed on these things, these things that we are writing down. and that is why people wrote them down separately as important notations. But the most important thing is that everything is just computed from the problem data, there is nothing external that we have to bring into. It is called the reduced cost coefficient. So, then these names were obviously given and became in vogue. Obviously, I cannot pinpoint you who had given these names, but it is usually taken like this. Okay. Another notation which is important is Yj is B inverse Aj. So, the jth column I am multiplying by B inverse, so I am transforming the jth column. So, it is Y1j, Ymj are the m elements. So, this is called the transformed column of A, transformed column, jth column. So, it was Aj, now the transformed column is Yj. Now, let us figure out a condition for optimality. So, now we will try to prove that under a certain given condition we will get an optimal solution, that is we will guarantee that an optimal BFS has been reached. So, sufficient condition for optimality. Now, this cost row vector I would again remind you, because there people might be so conversant with writing things as column vector. C is equal to CB Cn. So, this part corresponding to the basic part and this is the non-basic part. Now, just look at the cost coefficient in the reduced cost coefficient only for the non-basic part. Now, it is CB B inverse, not, if you look at the reduced cost coefficient in the last, it was CB B inverse A, but here I do not want whole away, I want only the n part of A, right. So, because I can write this A as B and n, so I can get the whole thing divided into two parts. So, one will be C minus this and another will be C minus that. So, I just this C would CB minus that, Cn minus this, because this can be written as CB minus CB Cn and this can be written as CB B inverse capital B. So, which is I, so it will become CB minus CB and then I would have C bar n. So, I will just work it out carefully. So, now you might ask me, what about C bar B? So, that would give you C bar, the total reduced cost coefficient, it is 0 actually. How? Because you see I can write my total reduced cost coefficient as C minus CB B inverse A. So, this can be written as just as above CB Cn minus CB B inverse A is divided into B and n. So, this can be again done through simple matrix manipulations. CB B inverse, so there will be a vector which consists of CB B inverse B, CB B inverse n. So, this is CB B inverse B is identity matrix. So, CB into identity matrix is identity. So, it is CB Cn minus CB B inverse n. So, 0 CB minus CB and Cn minus CB B inverse n. Now, this is C bar. So, C bar if I write as CB bar and Cn bar, which is equal to 0 Cn minus CB B inverse n. So, we will immediately have Cn bar, we will immediately know that Cb bar is 0 and Cn bar is Cn minus Cb B inverse n. So, it is the reduced cost coefficient associated with the non-basic part which gains more importance in telling you whether the current BFS is optimal or not. So, let us see. So, what is that sufficient condition? Sufficient condition is the following one. Sufficient condition is Cn bar is greater than equal to 0, that is Cn minus Cb B inverse n is greater than equal to 0. So, this is my so if I look at the reduced cost coefficient corresponding to the non-basic components of the BFS, then if all of them are greater than equal to 0, then I have reached my optimal solution, that is the current BFS is optimal. Now, again go back to writing Ax equal to B, which can be written as using the partition Bxb plus Nxn is equal to B, or Xb is equal to B minus Nxn, or Xb B inverse Xb. So, Xb is equal to B inverse B minus B inverse Nxn. Okay. Now, observe that B inverse B we have already given the notation B bar, or Xb equal to now Z, consider any feasible x. So, this is true for any feasible x. X in C. So, let me compute Z of Cx. This gives you CBXB, Cnxn, just the separation. Cb, what is Xb? It is B bar minus B inverse Nxn plus Cnxn. So, I will write Cb B bar, which is B inverse B, minus Cb B inverse Nxn plus Cn Xn. But Cb B inverse B is the optimal solution, which I call Z naught. So, Z naught is the optimal solution. Z naught is a, I should write Zb. So, Zb is the optimal value to the current basis B. So, Zb is the objective value, or not optimal value, I am making a mistake in my speech, objective value when basis matrix is B, which is the case. Now, once I know this is, I can now combine these two to write plus Cn minus Cb B inverse N Xn. So, what I get is Zb plus Cn bar Xn. Xn is greater than or equal to 0 because x is feasible and Cn bar is greater than equal to 0. So, whatever feasible set you take, for feasible, whatever feasible element you take from C, that is whatever x you take from C, the feasible set to LP, the objective value at that feasible point Cx is always bigger than equal to this value Zb. So, and Zb is equal to Cb into B inverse B. So, Zb is actually an optimal solution, and hence the current basis B is the optimal basis, and x equal to xb 0 is the optimal solution. because you see if I put x n equal to 0, then z is equal to z b. So, and that corresponds to the x when x where x n is equal to 0, right. So, here you see I have proved that if this, because C n is greater than equal to 0 because of this condition, z b is the optimal value, and z b is optimal value. Why? Because z b is the value of z at x b, which is b inverse b, and x is any feasible point. So, the optimal value at any feasible point is bigger than the optimal value at the particular BFS, and hence the particular BFS is optimal. So, it implies that x equal to x b 0 is optimal. So, we know how to check optimality. The optimality is checked by checking. So, if I just check C n bar is greater than equal to 0, I know current BFS is optimal. Now next question is how to check unboundedness. As the problem itself does not have a solution, how will you check that? And the beauty is that there are methods to check it directly from the problem data. That is why linear programming is so beautiful. So, as before, B is my feasible basis, IB is the index set of basic variables. Now, we will be really concerned with the non-basic part. If there exists an index j element of j set minus IB, that is the non-basic part, such that Cj minus Cb B inverse Aj. So, basically this is the reduced cost coefficient corresponding to the jth position, the jth vector in this set. This is strictly less than 0, showing that optimality is not reached, that is C bar n cannot be greater than equal to 0 if one of its, this vector C bar n greater than equal to 0 means all its components are greater than or equal to 0, but if one of its components are strictly less than 0, it cannot be, so current BFS cannot be optimal. Cn greater than equal to 0 implies current BFS is optimal, right. If current BFS is not optimal, you will always get this, right. So, if current BFS is not optimal, this will always occur. This is very, very important, that there would be some j for which this would occur if current BFS is not optimal, because this implies current BFS is optimal. If current BFS is not optimal, something like that will occur. So, if current BFS is not optimal, this will occur. So, once this sort of thing is occur, we should be see that here there is a crack. This is not an if and only if condition, that if the current BFS is optimal, then this will always be true. It says that if this is true, the current BFS is optimal, right. So, it is not a necessary condition, but if I have one of these to be that this is greater than not greater than equal to 0, then we cannot be sure whether the current BFS is not optimal, but if the current BFS is not optimal, it will give you something like this. So, once we have something like this in the algorithm, we try to be cautious, we know that possibly we have not reached the optimal and make a trial to go to the next point. And suppose these conditions are satisfied 1 and 2, the transform jth column, that is Yj, which is B inverse Aj, is less than equal to 0. So, there is a particular index j for which this happens. If this two happens, then LP is bounded below. This is a very important result. Just by checking the problem data you can tell, or just by looking at the problem data you can tell whether a problem is unbounded just after you make one iteration. So, how do we go to prove this? So, our next effort would be to prove this. Now, how will we do the proof? What we will do is that we will find a sequence of points or a continuous gathering of points. So, we will find a sequence of points such that those sequence of points is feasible. At the same time, if I compute the objective values at those particular points, then my objective value will continuously decrease and keep on decreasing without end and go towards minus infinity, showing that my problem is unbounded. So, I define a very x lambda is defined for lambda in the real number line R. So, now x lambda is also partitioned into two parts. In the same way x is partitioned, I partitioned as x b lambda and x j lambda, sorry x n lambda. This is the way you should partition it. So, x b lambda I define as follows. Now, x n lambda has two parts or j minus I whatever, n instead of n you could write j minus I b whatever, does not matter, I am just n is a better symbol. So, what happens when I am in the non basic part? So, then x j is lambda, x j lambda is equal to lambda and x k lambda is equal to 0 for all k which is in j, which is in this index set j minus I b, which is in the non basic part, right, n basically this is n if you want to write. So, and k is not equal to j, and k is equal to j, that is then x j lambda is lambda, otherwise this is 0. Now, b inverse a j I have assumed to be less than equal to 0. So, this is negative and there is a negative sign. So, this makes it positive. Now, b inverse b, x being a feasible element, right. So, b inverse b is a value of the objective value at the current basis. So, if you have taken any x which is optimal obviously, then b inverse b is the x b part. So, there is a BFS and there is a x b part. So, if b is a feasible basis, so b in feasible basis means b inverse b is greater than equal to 0 by very definition. So, which is basically nothing but the x b of the BFS associated with this basis b. So, this is greater than 0, this is negative, this is less than equal to 0 and there is a negative sign. So, this makes it greater than equal to 0 and this is greater than equal to 0 because b is a feasible basis. So, this would imply that x b lambda is greater than equal to 0 for all lambda greater than equal to 0. So, that is in general x lambda, because this is lambda greater than equal to 0 and this is 0, is greater than equal to 0 for all lambda greater than equal to 0. So, when lambda is greater than equal to 0, this negative and the negative of this makes it non-negative and this is already greater than equal to 0 because b is a feasible basis. So, this is what we have. Now, we have to prove, so we have proved one part of the feasibility of x lambda. So, we will show that if we compute the objective values at each of these points, the objective values will continuously decrease as lambda goes towards infinity. So, now I have to compute a x lambda to show that x lambda is greater than equal to 0 is guaranteed. Now, I want to show that it is also feasible. So, b x b lambda plus n x n lambda. So, this is nothing but b. What is x b lambda? X b lambda by definition is b inverse b minus lambda B inverse Aj. So, now for me now lambda is greater than equal to 0, because that is when it is feasible. So, our lambda now is obviously greater than equal to 0 plus n, and now x n has two parts. So, at the jth part it is 0, and at the jth part, jth component is lambda and rest is 0. So, basically n into x lambda will give me lambda into Aj, the jth column in the nth part, okay, and the remaining part is obviously 0. So, here I have B inverse B minus lambda B inverse B Aj plus lambda Aj. So, this will give me B inverse B is B minus lambda B inverse B is identity, Aj is Aj plus lambda Aj, which is B. So, x lambda is feasible. Now, obviously for lambda greater than equal to 0, for any lambda greater than equal to 0. Now, we are given the following, that Cj minus Cb B inverse Aj, that is the reduced cost coefficient, one of for the jth column corresponding to the jth column, is strictly less than 0. Now, what is C of x lambda? I want to compute this, that is Cb of xb plus Cn of xn. Now, this would give me Cb xb lambda is again B inverse B minus lambda B inverse Aj plus Cn xn. Okay. Xn, what is the xn? It is only lambda at the jth position, and all other positions it is 0. So, it will become nothing but lambda times Cj, where the corresponding jth position here. So, Cb B inverse B minus lambda Cb B inverse Aj plus lambda Cj. So, this is Cb B inverse B plus lambda into Cj minus Cb B inverse Aj. Now, I know that this is strictly less than 0. Now, this is fixed, this is the objective value at the current basis. Value at the current BFS. Now, this is negative. Now, if I make this positive, I can keep on making positive, x lambda would still remain feasible, but this value would go to minus infinity, because this is negative and this is positive, negative fixed negative number, and this is a positive number I am making large and large. So, this will become negative and continue to go down as lambda tends to plus infinity, goes up to plus infinity. So, with this we end today's talk here. We have two interesting conditions. One tells you when you know that you have optimality, and another tells you that okay, if this and this both are true, then you have a. So, if this is true, that okay, if one of these is strictly less than 0, you know that the current BFS is not optimal, because you take one lambda and I show that this is negative. So, this whole thing is less than, see, if Cj Cb B inverse Aj is strictly less than 0, if it is given to me, then C of x lambda for that particular lambda is equal to Cb B inverse B plus lambda times Cj minus Cb B inverse Aj, because this is negative and this is non-negative. Suppose I take lambda strictly bigger than 0, then also x lambda is feasible. So, for such a lambda, what I will have here is that this is negative and this is positive. So, this whole thing would be negative. So, this whole thing would be strictly less than Cb B inverse B. So, I have found a feasible point whose objective value is strictly better than the objective value at the current BFS. So, the current BFS cannot be optimal. So, when you are doing the simplex method, once you find a column of the negative of the non-basic part at which the value, the reduced cost coefficient is negative, you are sure that your optimality is not reached. You can have a feasible point whose objective value would be better than your current BFS. So, you have to go for a new one. Then you check whether B inverse Aj is less than equal to 0. For all the columns in which you have this, all the columns in the non-basic part, when you have this, you have to check also whether B inverse Aj is less than equal to 0. Then if there is one j for which this is true, then that will be a guarantee that from this result that the problem is unbounded. If none of them, if all of them are strictly bigger than 0, then we do not have an optimal solution, but the problem is not unbounded and we can proceed. Problem need not be unbounded and we can proceed. Not, we cannot guarantee it is not unbounded, but from this there is no information which tells me that it is unbounded. So, I can then try to proceed. So, tomorrow we will start with the exact procedures or the updating techniques used in simplex method. What does the simplex method do? You have a current basis, if it is not optimal, go to a new basis which could be optimal, or where the function value is, you have to go in such a way that the function value is strictly less than the function value earlier. So, that is exactly what we would show in our next lecture. Thank you very much.